Hi and welcome to this next video on differentiation. This one we're looking at how we differentiate logs, specifically the natural log. Now to do this we're using chain rule, and hopefully you appreciate that how useful chain is to be able to differentiate. We've used it to differentiate polynomials, exponentials, we're now into logarithms. The big one we've got to do after this is trig functions. But chain rule is a fantastically useful thing for being able to help us deal with all these different or differentiation of all these different forms of functions. So, log functions. Here we go, and it is the natural log function is the one that we're going to be working with. So here we go, let y equal ln x, and therefore if I reverse that I get x equals e to the power y, so that's just kind of the reverse process of having it in log form. And so now if we do dx dy, we know that result because e to the power y just remains as e to the power y. And we're aiming for dy dx, and we know from previously that dy dx is just 1 over dx dy. We've got dx dy here, which is, so we've got dy dx is 1 over e to the power y, but if you have a think about where we started, over here, e to the power y is just the same as x. So let's just do that substitution, and what we end up with that is that. And that one is a massively useful result, an incredibly simple one as well, and fairly unexpected. When you differentiate a log, you just get, when you differentiate a natural logarithm, you just get 1 over x, which is hugely useful for differentiating and also massively useful for for integrating as well. So let's have a look at how we do some differentiating logs. And again, what we're looking at here for these particular ones, I've just stuck to linear ones. And again, it's this idea of function within a function. We've got a linear function, ax plus b, sitting inside a ln function. So chain rule is always going to be useful for functions sitting within functions. So here we go, y equals ln 2x plus 1. Now we know our basic result for differentiating a ln function is 1 over x, but let's have a look at what's going to happen. Let's do a formal chain rule on this one. So there's the obvious substitution that we're going to use. du dx equals 2. That gives us y equals ln u. That's the result we know because that gives us dy du equals 1 over u. And then so bring those two things together. Dy dx is du dx times by dy du. So we end up with that. And then finally the last thing to do would be to reverse our substitution, and so we end up with 2 over 2x plus 1. Notice what you've got here is essentially f dash of x, or the differential, over the original function. Now, let's have a look at this one. Now, we're going to go through it. You might think, well, this is all a bit obvious. Why are we doing the same thing again? Well, there's a bit of a sting in the tail with this one, so let's just work it through and see what happens. So there's our substitution. Du dx is 4, y equals ln u, dy du is 1 over u. Bring them together, we end up with 4 times by 1 over u, which is 4 over 4x, and this is where you've got to be incredibly careful because look what's going to happen here. Those 4's are going to cancel, and you end up again with just 1 over x. So when you differentiate ln 4x, you get exactly the same result as if you differentiate 1 over x. And it's amazing how many times that that result catches people out. It is a slightly counterintuitive one, but you need to make sure you're aware of it. And if you're aware of it, then you can deal with it. That one never really makes a massive amount of sense in my head until I do it another way. And so I'm going to basically do exactly the same thing again, but do it used slightly differently, because this way seems to be just a little bit more intuitive for me. What I'm going to do is take my ln 4x and write it like this, using my basic log laws. So we've got ln 4 plus ln x, and now if I differentiate it in this form, ln 4, that thing there is just a constant, so that just disappears, and now we've got 1 over x when we differentiate ln x. So there you go, there's your dy dx equals 1 over x. Exactly the same result, done in a slightly different way. That second way just makes slightly more sense to me. But let's say it's entirely up to you, but you just need to be aware of it. And if we now have a look at it in its general form, so y equals ln ax plus b, let's go through it. So there's my substitution, there's the du dx, leaves us with dy du is 1 over u as ever. Bring those two things together, and there it is, essentially again, the differential over the original result, also the original function itself. And then that one, particularly useful for integrating when we come to start integrating things in fractional forms. And also you'll notice that we don't get any cancelling out going here because of the plus b, so we can't just start cancelling out the a's and leaving us with 1 over x. So that one does work in the way that you want it to. And there we go.